Hello, welcome to this lecture on curves. So in this lecture, we'll learn about regular curves and how to reparameterize a curve. So let us begin. So a parameterized curve alpha from an interval to Rn is said to be regular. So if this alpha is differentiable and alpha prime t is not equal to 0. So for all t belonging to this I. Okay, so where this I is an open interval. So this is the definition of this regular curve. Okay, so if I draw a picture, so this is my say alpha t. So alpha t, it is a point in Rn, and I have taken this alpha prime t. So this will be tangent to this curve alpha. So this is my curve alpha. And here, because I have taken this I to be open interval, so you'll not get this endpoints here. So I have taken I to be open interval because I want this alpha to be differentiable. Okay, so now I have taken this point alpha t, and so this alpha prime t, so this vector I have taken. So this vector, which is tangent to this curve, so this is not equal to 0. Okay. So let me also define. So what do you mean by tangent vector? Or it is also called velocity vector. So if I take, so let alpha be a differentiable curve. So then, so alpha prime t is called the tangent vector or velocity vector uh, of the curve alpha at the point alpha t. Okay, so alpha is regular if the tangent vector at each point is not equal to 0. Okay, yeah. So this is the definition of regular curve, and so example. So if I just take, so let us take let alpha t equals to uh, cos t sin t comma t. So this is a curve in R3. So alpha prime t, so this is equal to your minus sin t cos t 1. So therefore, so this norm of alpha prime t is not equal to 0. So this implies that alpha prime t is not equals to 0 for all t. So this implies that alpha is a regular curve. Okay. And what can be a non-example? So let us take, let alpha t to be equal to t square t cube. So alpha prime t is equal to twice t, 3t square. So alpha prime 0 is equal to 0, 0. Okay. So therefore, so this alpha is not a regular curve. So alpha is not regular at t equals to 0. Okay. So now let me give you the definition of arc length. So let us begin with a differentiable curve. Let alpha I to Rn be a differentiable curve, and also let us assume, so let us assume that this alpha prime, this is the derivative of this alpha, so this is also continuous on I. Okay, so now let us fix a point t naught belonging to this I, and now define st to be equal to this integration. So t naught to t integration of this norm of alpha prime t tt. Okay, so what is this s it is giving? So suppose we have this curve alpha, and suppose this is my point alpha t naught, and if I take alpha t here, so this uh, s of t, it is basically the length of the curve between this t naught and t. Okay, so note that, so this s, so now it is a function from this interval to r. Okay, so s is a function from interval to this r, and if we take this alpha to be a regular curve, so if alpha is regular, okay, so then this alpha prime t is not equal to 0. Okay, and norm of alpha prime t, it is always greater than 0. So uh, so s prime t is equal to norm of alpha prime t. Okay, so okay, let me write down. So if alpha is regular, so then alpha prime t is not equal to 0 for all t. And if I take the derivative of this s, so s prime t is equal to your norm of alpha prime t, so which is always greater than 0. So this implies that this function s, so s is strictly increasing. So s is a strictly increasing function. And also we call sometimes this s to be this arc length parameter. Okay, so we'll see all these things in a moment. Uh, why we call this s to be arc length parameter. Okay, uh, so we'll be now doing reparameterization of a curve. Okay. Uh, so a parameterized curve uh, let us call it to be gamma tilde defined on this open interval is said to be a reparameterization of the parameterized curve gamma. Okay, so if there is a bijective differentiable map phi from this interval a tilde b tilde to this open interval ab such that this phi inverse is differentiable and uh, so this gamma tilde of t tilde is equal to gamma of phi t tilde. Okay, so for all t tilde belonging to this interval a tilde b tilde. Okay, so this condition it says that, so if I have this diagram, so phi tilde it is a map from uh, this open interval a tilde b tilde to ab, and so gamma tilde is defined on this open interval and gamma is defined on this open interval. So this diagram commutes. Okay. Okay. So this is the definition of reparameterization. So note that, so trace of gamma tilde is same as trace of gamma. Okay, so only you are changing the parameterization, so the image it remains the same. So this gamma tilde and gamma, you can think it as a same curve, but only there is a change in the parameterization. So the image it will be same. Okay. So for example, so let us take a simple example. So let gamma t equal to your cos t sin t. Okay, and I can take this gamma tilde t tilde to be equal to your sin t tilde cos t tilde. Okay, so if I take this thing and phi tilde t tilde is equal to pi by 2 minus t tilde. Okay, so then gamma of phi t tilde is equal to gamma tilde t tilde. Okay, so that is very easy to check this thing. Okay, so now let me make one proposition. So suppose you take a regular curve and you reparameterize it. So then the reparameterized curve will be again regular. So any reparameterization of a regular curve is regular. Okay, so how do you show this thing? So let so alpha tilde be a reparameterization of a regular curve alpha. Okay, so this means that so this implies that so there exists a uh, differentiable map, bijective differentiable map phi from this interval to the interval AB such that phi inverse is also differentiable. Okay, so and so what you have, so alpha of phi t tilde, so this will be equal to your alpha tilde t tilde. Okay, so therefore, so now if I take the derivative, so let us take the derivative of this alpha tilde. So this will be equal to alpha prime phi t tilde. Then you have this scalar multiplication d phi t tilde. Okay. So we know that this curve alpha is regular. So therefore alpha prime phi t tilde. Uh, so this is not equal to 0. So this is not equal to 0 means now here it is a 0 vector. And so this phi is differentiable and phi inverse also exists and it is also differentiable. So this also tells that this derivative of phi, it cannot be 0. So this is not equal to your 0. So this tells that alpha tilde prime t tilde is not equal to your 0 vector. So therefore, so this alpha tilde is regular. Okay. Okay. So now, so this already I have said this thing. So suppose, so let me write it as a proposition. So let alpha be a regular curve and also assume that and assume that alpha is smooth. So let us, for convenience, let us assume alpha to be also smooth. So then, so this ST is this following integral. So then ST is a smooth increasing function. So increasing part already we have seen. And because alpha is smooth, so S will be also a smooth function. Okay, all right. So now let us observe this thing. So this S, uh, so ST, it is this integral T0 to T uh, alpha prime T dt. So suppose this, so alpha is defined on this open interval. Okay, and so let us take, so T0 is in this interval, and let us take some point here, your capital T. So, so now note that, so if I take this, so okay, so S of T0 is equal to your 0. And what is my S of this capital T? It is the length of alpha restricted to this closed interval. Okay, all right. And uh, so we have seen that this S, it is an increasing function. So it is an increasing function from this closed interval to this closed interval starting with 0 and ending with length of alpha restricted to this closed interval. Okay, so S is a function, increasing function from this closed interval to this closed interval. Okay, and S is also smooth if I take this alpha to be smooth. Okay, so therefore this S inverse also exists. So S inverse, it will be a map from this closed interval to the closed interval T0 comma capital T. Okay, so note that we have started with alpha, and so this S invert, it is a uh, differentiable. So S inverse is a differentiable map. So therefore, uh, so we can have this picture also here. So S inverse, it is a map from this interval to T0 comma capital T, and alpha is defined on this interval. So alpha restricted to T naught capital T is defined here. And we again have this map. So this is basically alpha compose S inverse. Okay. So therefore, so this diagram will compute. So therefore, the composition is composition alpha compose S inverse. It is a reparameterization of the curve alpha. And so we call it, so alpha compose S inverse is called arc length reparameterization of this curve alpha. Okay. Okay. So now note this note this fact. If I take the derivative of this alpha with respect to the arc length reparameterization, so we'll get that derivative to be of norm 1. So we'll get it to be of unit speed curve. So let me just write down the definition of unit speed. So what do you mean by unit speed curve? So alpha I to Rn, which is differentiable, is said to be a unit speed curve if so norm of alpha prime t is equal to 1. So for all t belonging to I. Okay. Okay. So now let us make this following proposition. So a parameterized curve has a unit speed reparameterization so if and only if it is regular. Okay. So suppose you are given a regular curve, so it can be always reparameterized in a way such that it will be a unit speed curve. Okay. So let us see how to do this thing. So let alpha be a regular curve. Okay. And let us take, so let us take a closed interval CD inside this open interval AB. Okay. And so this alpha compose S inverse. So this, in fact, it is a map from length of alpha restricted to CD to this closed interval CD. Okay. So here note that this ST is the following integral. Okay. So T is varying from C to D. Okay. So this alpha compose S inverse, so is the arc length reparameterization of alpha restricted to CD. Okay. Okay. So now let us take, so let U belongs to this interval. Okay. So let us take U belongs to this interval. So now if I take the derivative of this alpha compose S inverse U, so this will be uh, alpha prime of S inverse U and then we have this following scalar multiplication ds inverse du. Okay. Okay. So u I have taken in this closed interval 0 to length of alpha restricted to CD. So u will be equal to st, okay, for some t belongs to your CD. Okay, all right. And also note that so this uh, so ds dt, so this is equal to your norm of this alpha prime t. Okay, yeah. So therefore, so this derivative of this alpha compose S inverse u. So this is equal to your alpha prime t. Okay, and so what is your ds inverse du? So this is basically uh, 1 by norm of alpha prime t. Okay, so this you can check. All right. So therefore, so what we have, this norm of this derivative is equal to your 1. Okay. So norm of this derivative is equal to your 1. And so what we have done here, so if we take a regular curve and if I take the arc length reparameterization, so with respect to the arc length reparameterization, it will become a unit speed curve. And converse is obvious because if I take any unit speed curve, so uh, norm of the tangent vector is equal to 1, so it will the tangent vector is not equal to 0, so therefore it is regular. Okay, so I'll stop here. So we'll continue with this in the next class.